that introduction said some important things, I think, which is spending 19 years at IBM is actually an achievement, and yet I managed to escape with time off for good behavior. So now I am returning to academia, but Rosie is not an academic project, and so that's why you should listen to me today. Okay. This right here is a little snapshot of something from Stack Overflow, and you could argue pretty successfully, not completely maybe, that nobody writes regular expressions anymore. We all go to Stack Overflow, and if you wanted a regular expression for like IPv6 addresses, for instance, you could just go here and find it. And I looked at this a long time ago, and I thought, you know, this doesn't actually look too bad. It's kind of dense, but not too bad. And then I realized this isn't the whole expression. So I started to scroll. And scroll. So now, okay, so even though this is a really, really long regular expression, if it does the job, then you didn't have to write it. You could copy paste it from here, and everybody's happy, right? And there are like 75 comments saying how wonderful it is. And then there's this one, which says, I found a little bug. This comment does not provide a fix. And I can imagine why. It would be difficult to find the thing that's wrong in this expression. So I think we can do better than this. We can do better than Stack Overflow and such places when we want to store a bunch of regular expression-like patterns. And we can also do better than searching for these and trying to debug them or trying to maintain them when we do find a bug. And so this project, Rosie Pattern Language, which looks a lot like regular expressions, under the covers it's a little different, and I'll spend like the next 10 minutes convincing you that regex are fragile and limited. But this project came out of a job I did at IBM where we were mining data from a bunch of DevOps tools. So when IBM introduced its cloud, how many people knew that IBM has a cloud? Okay, that's more than normal. When IBM introduced its cloud, it introduced a set of DevOps tools, and this is just like the first 20 or 25. When I left IBM last year, there were close to 100, and all of these tools were integrated into DevOps workflows that you could run easily on the cloud. And all of these tools, of course, generate what some people have called digital exhaust. There is a bunch of data that is logged and stored for perhaps future use, or perhaps for just taking up disk space. And we could use that data to make predictions about your code base that might help your developers. So we can tell you things about the velocity of development versus the velocity of creating new tests. We can tell you things about coverage trends, and we can tell you things about when a developer who is not familiar with a particular component does some work on a component. And so we can do things like recommend particular files for code reviews. And we could even do some bug prediction. That was a work in progress, but it was definitely coming along. But when we started this project, we had to do a prototype, and we had a team of 4 people. And the team had to write lots of regular expressions to take all of the data produced by Git commits and Jenkins logs and all of these other tools, and mine through them looking for which project was this part of, and which files and file names do they reference. And when you close an issue, does it reference a commit? And where exactly was that commit? And then later, who integrated it? And so we did a lot of data mining on mostly unstructured text data. And what we found was that regex technology does not scale very well. So because we were working on a prototype, we had one person writing in Python, one person writing in Scala, one person wrote in a sort of combination of languages, and I think one person actually wrote some PHP. but we don't talk to them anymore. So one of the things we found immediately was that we could not share patterns. So if you had a bunch of people, this was just a team of 4. If you had a bunch of people and somebody said, yeah, I already wrote a pattern to process the ISO 8661 date time format that all the log files use, well, you copy paste that from Python into Scala, and it looks like it works, but it turns out on edge cases it doesn't work because the regex languages are a little bit different. And when you have a lot of patterns, it becomes difficult to manage a collection. And then when the data volume and velocity are both high, there are performance anomalies in most regex engines. And often you won't hit them until you start using these for big data applications. The more expressions you have and the more velocity of data going through, we were processing like a terabyte a day. And the more data, the more expressions, the more likely that eventually you will hit one of these performance anomalies. And I'll show you what they look like. So that's where this Rosie pattern language came out of IBM. Since I started it on GitHub when we first open sourced it, now it's on GitLab. And of course, I have since moved to NC State, where I can be an academic again and have more fun. So the current approach to processing unstructured text of any kind or semi-structured text, is to write regular expressions. They're at the bottom of every lexical analysis tool, and they are the go-to technology, even for natural language processing. But I want to tell you 3 things about regular expressions, some of which maybe you know already and some of which maybe you haven't seen. Okay. Everybody probably knows that these became popular as tools in the 70s, right? Ken Thompson of Unix fame wrote a 1968 paper saying, hey, regex looked like a really powerful way to search through text for things like text editors and to make a command line tool, which later became grep. And these are all, so sed uses regular expressions, grep and egrep do, and these are all actually useful regular expressions. And I don't even remember what they do, and I wrote the slide. They are just not very readable. And as of a couple of years ago, there were like 25 very common regular expression dialects. And they're all slightly incompatible, meaning that you can write something based on the regex dialect that you know in your head, and it will work most of the time, but perhaps not all of the time. So point number 1, or in the countdown, number 3, regex are notoriously hard to read and maintain. We can do better, right? All of those command line examples were from the early days of Unix when every keystroke was a valuable commodity because that keystroke had to go down a serial line from your terminal to a mini computer, get processed, and something had to come back, right? Nowadays, we have highly functional IDEs that do all kinds of fancy stuff for us. We don't need to count keystrokes anymore. So we can definitely do something better with syntax. Okay, in the countdown, point number 2 about regular expressions. We don't have to cut and paste, as in my Stack Overflow example, expressions like this in order to not write them from scratch. We could, in fact, say, let's store these things once we know that they work in a file, and we can have namespaces. And since this matches a date in a slashed format, we can have a namespace called date, and we can have many date formats, and we'll just call this one date.slashed. And we could take a bunch of different date formats and put them together with a series of ORs, or alternations, and say a date in any format is either a slash date or dashed, or it's in this ISO format, or it's in this other format. And so we do things like this. So we store patterns in files, and then we let you compose new patterns out of them. There is at least one tool, Grok, that uses regular expressions in this way. It lets you build named collections of them. Grok is used in Logstash and in Elasticsearch. How many people have used Logstash or Elasticsearch? Okay. So the ELK stack became pretty popular. If you have a lot of log files coming through Logstash into Elasticsearch, you can experience performance bottlenecks because Grok can be a little bit slow. But it wasn't even performance that drove us to look at Grok as a possible solution to our problem. My team looked at Grok because we could store regular expressions in files and give them names. What we found, though, was that Grok doesn't have packages. So it doesn't handle name collisions very elegantly. In fact, some versions use the first time you define the name, and some use the last definition of the name. There was no way to model dependencies, and at the core, you still have regular expressions. So you still have things like this. This is a diff. I apologize for the font size for those in the back. Although, actually, this slide's just a wall of text, so it doesn't really matter. But this is a diff of 2 different Grok files. And I dare you to spot the difference. Maybe in quoted string up at the top, we could find it if we looked carefully. But how do you find the difference in the IPv6 definitions, right? So we still had this problem where even if we use Grok, we'd be using regular expressions, and they don't play well with development tools, right? When you check something in on Git, it's using diffs, and this is what the diffs look like. So RPL, which I promise I'm going to show you soon, has a syntax that's more like a programming language. It's less dense than regular expressions, so you have to write a few more characters. But it reads like code with comments and white space, and it diffs like code. Okay, and the last thing I'll tell you about, which I saw some people nodding when I mentioned performance anomalies. In terms of the good, the bad, and the ugly, regular expressions are great in terms of performance. They're guaranteed to run in linear time if you actually implement regular expressions. But nobody does, right? Regular expressions were defined theoretically in, I don't know, it was Noam Chomsky. What was that, the 50s maybe? 40s or 50s? Nobody sticks to just the theory. The theory says you can implement these really fast, but in practice, nobody does. And Russ Cox pointed out a few years ago that the worst case exponential time strategy is the algorithm used in almost every popular implementation of Regex. And you can see this on your own machine if you type in a few examples. This example is in Perl. Which means it's write only, but if you try to read it, it's actually not that hard because the regular expression is just a bunch of A question marks followed by A's. And here's a more realistic example where we have some comma-separated data, and somebody's trying to skip over all the fields up to field 29 and then see if what's there matches gold. Both of these things trigger exponential behavior, and so the one on the bottom, instead of taking a fraction of a millisecond, takes 65 seconds. So what happens when somebody puts a regex like this into your data processing pipeline, and then eventually some piece of data comes in that resembles this CSV line, right? Instead of processing maybe one input every millisecond or less, you're now stuck for 65 seconds, which stalls your entire processing pipeline. Okay, so in RPL, one of the big differences from regular expressions is that RPL expressions are always greedy and always possessive. So if you've used regex enough to have come across those features in regular expressions, they are the default and primary behavior in Rosie, which means it is difficult to be accidentally inefficient. If you stick to the non-recursive, the core part of RPL, it is really hard to write something that runs in exponential time. Essentially, to do it, you have to write an expression that's exponentially long, which means you can obviously see this very long expression may take a very long time. Okay, so finally, I get to tell you what the language actually looks like. Here is a file that defines all of the JSON standard. So you don't have to parse JSON using RPL. There are very fast, dedicated JSON parsers. But just as an example, you could parse JSON with Rosie. And there are a handful of definitions here. True is bound to the string true, false to false, null to null. The definition of key and string are word.dq, which is an imported definition from the Word package, which says I want to use a double-quoted string for that. JSON numbers happen to be defined in the number package. And then here's a recursive grammar that defines JSON values and object members, objects themselves, and arrays. I think what's nice about this is that it's fairly easy to read. Like, we're used to reading and debugging programs, and the syntax looks more like a program. So even though this is not a programming language, it is not Turing complete, there are no control constructs, it's a pattern language, but one that looks enough like a programming language that we can have some hope of debugging. There are comments, modules. This one defines the JSON module. You see that you can put white space anywhere. There's also unit tests. So here in the comments at the bottom, there are a number of tests that say what kinds of strings should be accepted and rejected by these definitions, which means you can run these tests. They're all executable. You can run them at any time. So if you decide you need to change something in one of your expressions, you can immediately run all of these tests and use them as regression tests to see if anything changed, see if you broke anything. One of my colleagues who's a software engineering researcher, she says that her estimate is 17% of regular expressions in code are ever tested. In other words, if you look at just coverage, only 17% of the lines that use a regex are actually covered by a test. And most of those, the vast majority, are only covered by a positive test, not a negative test. And so here, I think we're including something that is really important if you're doing data mining, which is to have a library of tests that you can rely on. Yeah, question.
Is the test expressed as a comment, or you just show it here as a comment?
The test is actually written in the comments, but it's executable. So tell Rosie, run all the tests found in this file, and it will run all of these. Oh, and now we wait while Keynote builds all this again. OK. After I got some traction with Rosie within IBM, we decided to open source it because tools like this are more useful the more people use them, right? There's a network effect. If we are all writing some patterns that are useful to us, and we post them online, anybody could download the RPL files and make use of patterns written by other people. So the idea that we might share this with the world and release it as open source under the MIT license led me to start tweeting about RPL in a series of rather obnoxious tweets called, "Can your grep do this?" And here's one. You don't have to write the pattern for net.url. You can curl the Google homepage, which is 400 lines of HTML, and just say, give me the submatches of net.url, and get out just the URLs that are found on Google's homepage. And here's another one. Here's a pattern that you can type on the command line. Match word.any followed by any number of network addresses. And as input, I gave it the file testresolve.conf. I was originally using my own etcresolve.conf, but it doesn't have enough interesting things in it, so I made a test one. I don't even know if you can put IPv6 addresses in resolve.conf. I would expect so, but I put that in there for an example. And of course, you can set the output to be any kind of color you want. So I can say I want all the IPv4 addresses to be blue and bold. Why do we have color output? Because these tools are written for people, right? There's two interfaces really to every tool. There's the interface that runs in your data processing pipeline, where you might call Rosie from Go or Haskell or Python or some other language. But then there's also, like, how do you develop patterns? It's easier to develop patterns if you can access a command line or read a val print loop, and if you can see the output in a way that just makes sense to people. And of course, I had to create a package called all, which has a pattern in it called things. So I can say match all.things, and different colors are assigned to different kinds of patterns. So at a glance, you can see what kinds of things are in a file. You know, the green things are path names, and the red things are network related, and the blue things are dates and times. And if you wanted to look at this output in JSON format instead of color text, you just switch the output flag to generate JSON. And then you can see exactly, you know, which date time format is this, and what kind of path name did this match, you know, Unix or Windows, things like that. And here's JSON output. You get to see the line of the input that matched, and there's a nested JSON structure here, which includes submatches. So I was trying to match denoted hex. So find a hex number that is denoted as hex with a 0x prefix. And it found it, and a submatch of this is it matches num.hex. And here's another one that matches num.hex. So you can pipe this then into some other program. Okay, I do have more examples, but I wanted to give you an overview of how Rosie is built. There's an RPL compiler, which takes any patterns stored in library files, along with your patterns, and there's nothing special about these library files. So the JSON ones and the date time ones and all that are things that you could have written yourself, and you can edit the hell out of them if you want to suit your own needs. But they all go into an RPL compiler, and then the result of that is a program that runs in this little matching engine. Matching engine takes data, and depending on what kind of output you want, generates one of several different things on the output side. The compiler itself is written in Lua. How many people have heard of Lua? Okay. It is a popular embedded language, and that made it really good for this project, because now I can say, if you want to write your own output encoder to take a match and do something with it before creating output, you could write that in Lua. And if you want to write Rosie macros, shorthand for things that you write frequently, you can do that. You have to write it in Lua, but you have the power of a programming language then. And that's only needed at the compilation stage. Output encoders would be needed at runtime. If I compile just this matching engine, the matching engine's written in C. And if I compile just that, it turns out to be a library that's 50K in size. So it's pretty small, easy to link in to anything runtime. So when I was at IBM and I told them that we're headed towards a 50K runtime library, they said to me, you know, 50 meg is not all that small. And I said, no. I said, 50K. IBM is a large Java shop, so I think they've all forgotten what K stands for. If you do go look at performance, the runtime performance is pretty good because the matcher is written in C. And it's hard to compare what Rosie does with tools like grep, because grep is very specialized and Rosie does more. So I compared Rosie with Grok because we were using that in our ELK stack. And here performance it's time on the y-axis, and so performance is better if it's lower. And Rosie's down here, roughly 4 to 5 times better than Grok. Grok can run in Ruby and JRuby. When you run it in JRuby, you pay a few seconds of JVM startup time, but then it outperforms its pure Ruby cousin, which is not surprised. I mean, when you need speed, you don't go to Ruby. But more interesting, I think, than the relative performance is the fact that Grok bailed out, like with a seg fault, with a UTF-8 error. So there were some badly formatted bytes that were not valid UTF-8 in the input. This input was actual log files generated from programs running in the IBM cloud. So real data is not necessarily formatted UTF-8, which I'm sure you all knew, because just because, right? This is the real world. Everything is not always as you expect. So of course, Rosie handles this fairly gracefully. There's a nice Unicode package designed to handle all the Unicode categories in UTF-8 and even broken UTF-8. So then finally, one of the main problems we saw initially when we wrote regular expressions in our prototype was that it was really hard to debug them. And part of the reason was that we got all confused ourselves when debugging them because different people were using different regex engines. But part of it is just that it's difficult to debug. So we implemented a trace function in Rosie. And this box is going to fill up with text that you don't need to read. But here's the problem. We run the Unix date command, pipe it into Rosie, and tell it to just pull out the date part of this string. But it turns out the date part is not in the dashed format, right? It's in a different format. And so we're going to get a mismatch. But all we did was change the Rosie match command to a trace command. And now we get essentially a stack trace. We get a back trace of every attempt to match part of the pattern that you used against part of the input. And just like you don't have to know how to read a backtrace in a language that you're not familiar with, you don't know how to read this, but the fact that it exists means that as you work with the tool, you can see exactly where it failed and why. There's also a read-eval print loop, so you can develop interactively. You can see what patterns are already loaded. You can match things right at the command line. So here's a match command against the destructuring package. The destructuring package has patterns that pull data out of tuples. Your tuples might be parenthesized, they might have curly braces, they might have brackets, they might be space separated, they might have commas in between. The .try all tries all of these things in succession to see what works. And we actually integrated this into a data science analysis tool at IBM, and what we did was we fed the first few lines of data files into this, which destructured them, and then once we learned how they were destructured, we could automatically generate a pattern that processes the rest of the file without having to try every possible way. And it pulls out in the data field exactly the three things that were part of the input data. And I told you the tests were executable. This is what it looks like when you type Rosie test. And here's a path to a directory that contains a bunch of RPL files, and it runs all the tests. So these become part of your build process, right? You run all your regression tests, and in the process of doing this, all your patterns are compiled. And so a lot of errors that might happen at runtime in production are actually caught during build or during test. And in case anybody's interested, how many people have taken a theoretical CS course, computer science? Okay. How many people remember anything from their theoretical computer science course? Okay. It's usually a lot fewer hands. So regex is based on one particular formal automata model. And all PEG grammars, parsing expression grammars, Rosie is one of them, all PEG grammars can do everything regular expressions can do, plus a bunch more. So why do we need more power than regular expressions? Because over time, people have extended regular expressions in various ad hoc and non-standard ways. We can also support recursive pattern definitions, and that's one of the reasons people have extended regular expressions. They want to match things like all expressions with balanced parentheses. And this is what that looks like in Rosie. Now, you have to type more characters than if you want to do that in Perl. But like, why would you want to type this in Perl? And how would anybody ever understand what it did? You know? There are implementations of parsing expression grammars that are guaranteed linear time. The Rosie implementation does not guarantee linear time because if you write something that's recursive, it could actually take more than linear time. But if you stick to non-recursive things, you can get a linear time guarantee. Because expressions are greedy and possessive, there are some weird things that happen if you're used to regular expressions and you move to Rosie. So if I type match dot star followed by x, this will always fail, because the dot star will match everything and then never go back and reevaluate something less than that. This actually avoids a big performance issue in regular expressions. It avoids a lot of quadratic and exponential time behavior. Because we want this functionality sometimes, like consume everything up until you see an x, the way you would write this in Rosie is, while not looking at an x, consume a character, repeat that as many times as you want. That will run up until there's an x, and then try to match the x. Because this is a bit repetitive and Rosie has macros, we can write a macro, and this is one of the standard ones that's just find x. And find x expands internally into something like this. Okay, the syntax is very familiar if you're familiar with regular expressions. For things like Unicode, there's a collection called script and a collection called block, and there's for every Unicode category there's one of these, and there are patterns there defined. So you can say things like, this is a character class that matches underscore, space, and anything in the Greek script, and so it will match things like this. You can use Rosie in programs in a bunch of different languages. In the past, for earlier versions of Rosie, we have written bindings in Java and Lua and Ruby that are not working today because Rosie has changed in the 2 years since. So I aim to get those back up and going. It really helps to have people knowledgeable in those domains, because if I try to write a Ruby package, it's going to look like something entirely different from Ruby. But if anyone's willing to work on those bindings, I am happy to help, as are my students. So in conclusion, in my view, for the use cases that we were going for, we found Rosie to be faster, better, and cheaper. The return on investment really comes from going to an existing library instead of to Stack Overflow, right? Being able to reuse patterns and compose them into bigger ones, having unit tests and pre-compilation, and having the development tools to support it. Thank you very much.